Welcome. This talk is about the abstraction task provided by NOELLE. This talk is for my class Advanced Topics in Compilers that I teach at Northwestern University. I've decided to open these talks to everyone, even if they are not professionally made. We hope they will be useful for anyone interested in doing compiler research while taking advantage of the NOELLE framework. This talk is organized in 3 parts. First, I'm going to talk about what is a task in NOELLE. Then we're going to start looking at how to create a task, how to define a new task, and finally, how to invoke an existing task. Everything that we're going to talk about can be found in the module task under source core, and the header after install NOELLE is going to be under install NOELLE core task.hpp. Here is where you find all the public API about the abstraction we're going to talk about now. The abstraction task of NOELLE is a wrapper of a set of instructions S organized in basic blocks that are cloned from the original code. S is wrapped into a new function, F, and there is an environment E that includes the live in and the live out variables that S needs. So let's say, for example, we have an original code that looks like this, and this is a loop. This is the control flow graph of a function. Here we have a loop, and inside the loop there is a basic block where it has 4 instructions, I, J, K, and Z. Let's assume that we care about, for whatever reason, we care about the instructions J and K. And now we want to take these 2 instructions and extract them into a task. So therefore, in order to do that, we're going to have a function f that wraps the set of instructions S, which includes J and K, and then an environment E that are about the live in and live out variables of S as a set of instructions. So here in F, we are going to compose a set of basic blocks. In this case, it's going to be 1 that includes the instructions S. And inside these basic blocks, we're going to have clones of the set of instructions included in the set S. When we're going to create this function f with the clones, the task abstraction automatically is going to keep track for you of the mapping from the original code to the clone version. And finally, the environment is going to provide information about which variables are live in of S and which variables are live out of S. So you can use this information to decide how to fill up the remaining basic blocks that are going to get the live in values and also to propagate the live out values. F is called task body, and E is called task environment. A given task has a static unique ID that is an ID of the static version of the task. But then that task can be, you can create many instances of that static task, and each instance is going to have its own dynamic instance ID. The static ID is set by the task abstraction automatically, and instead the instance ID is a value pointer, and whoever is the designer of a given task, that person is the one that is responsible to create this value pointer and to register to the task abstraction. The task abstraction ignores where this ID is going to be stored or kept, or even if it's going to be kept. It's going to just keep track of it after the value pointer is registered to the abstraction. So then anybody else that wants to use that abstraction task can ask to retrieve the dynamic instance ID to be used at runtime. There are 2 tasks, sorry for the overloaded term. There are 2 tasks to define a task. First, we have to define the task, and then we have to invoke it. So let's start with the definition of a task. So whoever defines the task, the first step is to define the signature of the function f, which is the task body. So the signature is dictated by all the inputs that we need to invoke F. And also we need to, therefore, it's very likely that you need to have some kind of input or inputs that define the live in and the live out variables of the task. So you need an instance of the task environment that from which you can retrieve all the live in and the live out variables. The return type of the signature of F has to be void all the time. The signature is an input to the task constructor. So after you set it, to instantiate a task, you have to declare a signature and then cannot be changed after. So for example, let's assume here, let's go back to our example. Here we have a loop, again, with the instructions J and K, and we want to extract them into a task. Now, because there are live in and live out variables of this set S, then we as a designer of a new task, we decide that the only input we need is an object represented by or pointed by a void pointer. So in LLVM IR will be int8 pointer, and this object is going to contain all the live in and live out variables, in our case %v0 and %v2. So therefore our signature of the function is void as a return type because that's a constraint, and then one single parameter of type int8 pointer. In order to do that, we can use the type manager of NOELLE to find the right LLVM type to define the signature, and then we use the LLVM API to create a new signature with the function type get API. Now that we have the signature, we can create a task. In order to create the task, we also have to create the body. So the body of the task is composed by basic blocks, and as soon as you instantiate a new task, the body is going to be created for you with only two basic blocks. One that has a special name called entry basic block, which is the first code that is going to be executed when F is invoked. And also you have the exit basic block, which is the last code that has to be executed before leaving F. And those are constraints. These allow a user of a task to know exactly where is the basic block that is going to be executed no matter what at the beginning of the execution of the task, and the one that is going to be executed no matter what at the end of the task. Both basic blocks are empty when you create a new task. In order to create a new task and therefore create these two new empty basic blocks, you just invoke the constructor of the class task. You pass the signature of the task body, so the function F, and you pass the module where that includes the instructions that you're going to outline into the task. After you do that, therefore, our function is going to look like this, exactly like this. This is the control flow graph you're going to. Okay, of course, you don't want to create a task to have an empty body with only two basic blocks that don't do anything. So therefore, the task abstraction provides many APIs to help you to add code into the task. The simplest one, perhaps, is clone and add basic blocks that takes as input a set of basic blocks and a filter, a lambda function, that you can use optionally to define which instructions that are within the basic blocks that you pass as a first parameter you want to add into the task, and therefore which one you don't. Every time the filter returns true means you want to add that instruction into the task, otherwise false. In order to add, for example, all basic blocks of an entire loop inside the task, and therefore what that means is you take the whole body of the loop, the whole loop, and you outline it into its own function, and that will create that will be the task body. then in order to do that, you can, after you create the task T, you invoke clone and add basic block, and you take the instance of loop structure of the loop you want to clone, and you invoke the API get basic blocks, which return the set of basic blocks. And the filter is always going to return true, which means you're not filtering anything. You take all instructions within the basic blocks. And after this, you have a task with a task body that has an entire body, an entire loop of the original code. In this case, instead, we want to only add J and K. So let's assume we invoke the previous API with a filter more elaborate that only identify J and K and only add J and K. For every other instructions of the loop body, it's going to return false, therefore they're not going to be added. In that point, the result is to have a task body where you have a new basic block where it has the code that you have cloned, and automatically the task abstractions is going to keep track of the mapping from the original code and the cloned instruction. And this map, this table, can be accessed with the task API. Of course, therefore, now what is left is the code that we have to add just at the beginning of the task and at the end of the task to propagate live in and live out variables. After we do that, then the task abstraction is completed, and therefore the only thing left is how to invoke this task. So whoever defined the task is in charge to identify and instantiate the loop, the task environment as well. The task abstraction look at the task environment as a value pointer. It doesn't. The task abstraction itself doesn't help you in defining the task environment object. So you, as designer of a new task, you are in charge to decide how to lay out this object, where to put the live in and live out, and then you need to manually add the code in the task entry basic block and the task exit basic blocks that is coherent and consistent with the with your design decisions about the object that contain the live in and live out variables. So you need to decide the data layout of that object. Let's make a couple of examples. So this is the code we had before after adding the instructions that we care about, that we want to put in our task. But now as you can see, the task entry basic block and the task exit basic block they are empty. So we need to decide the code to add there to propagate the live in and live out, which depends on the data layout of the task environment. Let's make an example of a design decision, how this object needs to look like. So let's assume that we decide that we're going to have an array. The task environment is going to be an array with one entry per unique live in and live out variable. And let's assume that this array is an array of pointers. So the first entry is about the first live in variable, which is v0, but we don't include v0 in it. Inside the first entry of this array, we're going to have a pointer to another element that is v0. Okay? So the second element of this array is a pointer of v2. Let's assume that this is our design decision. So therefore, in order to be coherent with this design decision, the code that we have to add on the entry basic block of the task is we take this object that we just defined the data layout right now. So that is going to be the input of the task body, and the input is going to be called %e as a first parameter. So what we need to do here is, from here we're going to do a get element pointer instruction of LLVM to compute the pointer that points to the first element of the array, which is a pointer. We call this %p0. We loaded from it. What that means is that we have loaded now the address, the pointer of the second element, which is the pointer to %v0. Then we load from it, and now we finally, by doing that, we finally have the value that %v0 had just before invoking the task. Then, and in this way, now we have our live in value that we need to run the task body. And we call this %v0 prime to emphasize that this is a clone of the value of the original %v0. And now this %v0 prime is going to be used inside the middle basic block that actually does the computation we want. But also this code has a live out, %v2. Now we don't need to load the value of the live out. We need to store the final value into it at the end of the task execution. In order to do that, we need to fetch the pointer of the location where we're going to store the value of %v2. In order to do that, we do another get element pointer to get the second element of the array E, which is gonna include a pointer to %v2. So so we fetch this element with the get element pointer and we call it %p1, the variable that points to the second element of the array. By loading from it, now we have the pointer of the location where we're going to store the %v2 value, and we call this %v2p. At the end, when the execution is over, now we have to propagate the live out value outside the task. In order to do that, we're going to store the final value %v2 prime, the one we computed inside the task, into the location pointed by v2p. But let's now assume that we're going to make a different design decisions. Now the object E is an array, but is not an array of pointer anymore. It is an array of two elements, and these elements are directly the live in and live out variables. So the first element is v0 and the second element is v2. So now, to be consistent with these design decisions, the code we're going to add in the entry basic block and the exit basic block of the task is different. So in the entry basic block, we need to compute the pointer of the first element with the get element pointer. We call it %p as before. But now when we load from it, we don't load the pointer to v0, we load v0 directly. Similarly, for v2, when we compute with the get element pointer the pointer of the second element of the array, and we call it v2p, that's the only thing we need. We don't have to do any load because v2p already points to the v2, and therefore at the end we just store the last value v2 prime into v2p, and then it's done. Now that we completed creating a task or defining a new task, now let's see how we can invoke it. So a task is invoked by calling the function f, which is the task body. The code that invokes f needs to set up the memory instance of E, of the object E, that is consistently with the data layout chosen by the definition of the task. Now let's go back to our first example where we made the design decision to have the environment object E to be an array of pointers. Now in this case, we want to invoke this task while being consistent with this data layout. So how are we going to do it? Well, first we need to allocate this object of this array of pointers and also these elements that these pointers point to. Now, we could do this just before s, but if we do that, then that is going to be repeated between iterations of the loop, which is useless. So therefore, we can put the allocation part outside the loop. So we add a new basic block, and here we're going to add the code that allocate exactly that data layout that we discussed. So we call first we allocate the array of pointers, which we call it %le. Then we're going to allocate the two different object locations where we're going to store the value of %v0 and %v2. We call it %v0s as stack and %v2s as stack of v2, or the version of v2 that lives in the stack. Then Now we have the three objects, but now they're not connected. So now we have to connect them. So first we use getElementPointer to take the pointer to the first element of %LE, and then we store the pointer of %V0s inside this array element. We do the same thing for the second element. At the end of this new basic block we just introduced, we have the object that is outlined in memory exactly as it shows in the picture on the bottom right. But now the values inside %V2s and V0s, they are nonsense. They are not valid. So that's the only thing left to do. We need to add correct value inside the location pointed by V0s and pointed by V2s. But in order to do that, we have to do that just where these values are available and correct. In our case, it's always safe to add to take these values just before the code that you decided to outline into a separate task. In this case, just before S, so just before the instruction J. How do we do that? Well, we take the live-in value, or all the live-in values. In our case, we only have 1% V0. We take that and we store it into the memory location that corresponds to that live-in value, in our case %V0s. Then we invoke the function. Because live-out variables, they are value propagated after the task execution, so we don't have to do anything before the task. By invoking f, we execute the task. And then when the task is completed, then we can load the live-out variables and store them into whatever is the local variables that we want to modify. In our case, it was %V2 was the local, the live-out variable. So now %V2, instead of being set by k, is going to be set by the load that loads from the %V2s that includes the live-out value that is generated by the task. And of course, if you have these snippets of three instructions, the store, the call, and the load, then you can replace j and k with these three instructions. And then the original semantics is preserved. Of course, you may say, well, but now we replace two mathematical instructions with a store and a call and a load, which is it takes longer to execute. But this is just an example to show you how to do it. Of course, it makes sense from a performance point of view if S is bigger. Let's go now to the second example, where we decided the data layout to be an array of values, not pointers. In this case, we just need to allocate a single element, and we still call it %LE, and we just need to take the pointers of the two elements of the array. And then we store, as before, we store the live-in value inside the first element, and then we load the value of the live-out variable from the second element. With this, I hope this is going to help you, and good luck.